Already. Sid!
21.
This is always fun since I did these years ago. I don't know what the problems are. Find the speed of a cycloid at points where the tangent line is horizontal. So we have to find where the tangent line is horizontal. But that's where the dy dx comes in. So find dy dx. Where's my arrow? There it is. Set it equal to 0. And you can find where the tangent line is horizontal. Wow. And in order for this to be 0, the numerator's got to be 0, but the denominator can't be. Because if the denominator was 0, you would be undefined. So I end up with that. Yes?
Can you just explain like the first thing? So how is dy dx 4 sine t or 4 minus 4 cosine t?
Well, here's dy dt. So, well, here's y, I mean. So the derivative of this part, derivative of 4 is 0. Derivative of cosine is negative sine, so that cancels out the negative. So you get 4 sine t in the numerator. And then for the bottom, you got to find dx dt.
Oh, because it's y over.
Yeah.
Oh, okay. Nice.
And then you got the rest of the problem? Or do you want me to go on?
No.
Keep going? Okay. So now I know where it's going to equal 0. So then I use the formula for speed. And conveniently, we've got the derivatives up there. So it was a matter of playing around with this. And, I mean, I could have plugged in right there, but I wanted to simplify it down as much as I could. Could have really gone there, because we're not taking the derivative. I mean, the antiderivative. We're just doing speed, which is just the radical. But then it's a matter of plugging this in. And so plugging that in and playing around with it, this will end up hitting every time sine is 1. 1 or negative 1? 1 or negative 1. Yeah. So, but either way, you're in the absolute value, so it's going to be 8. Any other questions? Yes, Greg. 11. Show that one arch of the cycloid generated by a circle of radius r has a length 8r. All right. And I don't know if the problem said see example 2 or if I said see example 2. But anyway, here's what's going on in case you're wondering, what is a cycloid? So a cycloid is formed, it's kind of like the epicycloid that we looked at, but the epicycloid is a circle going around another circle. This is a circle just rolling on a straight line. So if you follow the path of one point on the circle, it's gonna just do a bunch of arches. To complete one arch, it's one rotation of the circle. So they must have given us the formula, or I got it from example 2, but are we okay with just where the formulas are? Like, that's kind of good. You don't have to know that. And what are we finding? Arc length or speed? We're finding length, okay, but I still started off with this part. So working through that, I get this. So is that okay, or do you want me to work through anything here? Okay, so then we can plug into the formula, and because it takes one rotation of the circle to go to make one arch, that's how I knew to make my limit 0 to 2 pi. And so then it's just evaluating this, and hey, look at that, it works out to 8r. What? I guess they were right. For once. Hey, you like my shirt? I actually forgot to wear it yesterday, but then I thought, oh, hey, this works out perfect, because do you recognize this? It's the Taylor series for pi that you guys found on that worksheet the other day. Oh, yeah. Any other questions on the homework? Well, then, let me have your homework. And guess what? Would you hate me if we didn't have a reality check today? Yes. Well, I'm going to be hated then, because we got a reality check today.
What kind of logic is that?
Look at that. Period.
Wait, I'm turning it
Over parametric equations. What?
I'm turning it homework A.
Okay.
Should I hand it with a tile or no?
Yeah. As long as it's labeled, it's fine. And I will pause the recording now. Any questions over this one? Kind of nice that that question got asked about the homework. Kind of refreshed our memories. Anybody want more time looking at this one? All right, ready for number 2 then? Hang on, I'm not ready. There we go. Now I'm ready. Number 2! Actually, yeah, I can fit both of them. There's 2 and 3. Any questions over it? Oh, Sid, yes.
Okay, so for problem 2, right?
Yes.
So we're finding the acceleration by differentiating the x and y with respect to c separately twice, right?
Yes.
Okay. How is that? Is that different from the other thing where it's like the speed is given as the derivative of the arc length? Is this the same thing?
Sorry, my ear itches. It's not the same thing.
Well, I meant if you get the speed by differentiating the arc length and differentiate that again.
Get the vector. I mean the velocity, not the speed.
Okay, yeah.
So. No, so yeah, the difference is the vector, which we haven't really talked about, but this is so much like, I was going around and around about do I want to do this one, but figured since it's a lot like finding the acceleration in terms of x and y, I'm going to wait until we get to vectors to further explain, but yep. Any other questions? Ooh, let's talk about polar then. So, yeah, we're going to do some notes. I need to sit down. Yeah. How about this crazy, like, there's wetness coming down from the sky this morning. Yeah. It was a storm. I know, right? I still don't understand out here calling. Seems like anytime there's any kind of precipitation falling from the sky, it's a storm. You don't know what a storm is out here. But oh well. I didn't have this ready. Sorry. Polar equations. Actually, I guess it's called polar coordinates. We're going to go with the book title. And we are going to talk about polar coordinates and equations. So there you go. So first, let's review polar coordinates. Now, you should have seen polar coordinates in STEM or pre-calc, depending on what you took. I know students that had STEM a couple years ago, even though that's when we went into closure. Oh, we did polar. But that's also the year that things went past no pass. So how seriously you guys took learning then, and how much you learned. And I don't know about trig pre-calc if they actually taught. Do you guys remember learning polar? Does that sound familiar? Okay, the good news is it's not hard. All right. No calculus today, right? Yeah, no calculus today. It's all just, what the heck are these things? Yes. So, you guys are used to what's called rectangular coordinates. These are also sometimes referred to as standard coordinates. So this textbook uses the word rectangular, but you might use other books or hear other people call them rectangular. And then we have polar coordinates. This is definitely the more common name for them, but sometimes they are called trigonometric coordinates. So just so you know. It's just two different ways of giving the location of a point in 2 dimensions. We're used to an x and a y. So, actually, I'm going to go ahead and I'm going to make a straighter line. I don't like that. Use our straight line tool. Okay, so I got these little dots I'll make use of here. So we're used to a grid. Ooh, missed. And assuming that my scale is 1 on both axes, I can put a point here, and you can give me the rectangular coordinates. At least you should. And if you're somehow made it this far, not being able to tell me the x and y coordinates for this point right here, well, good job. I don't know how you did it. What are the coordinates for point A? Excellent. Yes, 3, 0. And just for fun, how about this point right here, which we'll call B? What are the coordinates for that one? -3, -2, yes. So the way we're used to giving the location of this point is the x and the y coordinate, which tells you how far in which direction to go left and right, and then how far in which direction to go up and down, starting from the origin. Another way, though, that you can do this, actually, let me go ahead and put up here. So rectangular coordinates are given in x, y. Polar coordinates are given in the terms of r theta. Oh, now it's starting to come back. All right, so r theta, r tells you the radius of the circle that you're on, and theta tells you how many degrees around the circle you've gone. So I'm going to use this same plane that I've drawn, but what I'm going to do is I'm going to put a bunch of concentric circles starting with a center at the origin. So we have a circle with radius 1, a circle with radius 2. I don't like how that first one messed up everything. There we go. Circle of radius 1, a circle of radius 2, a circle with radius 3, and I'll go one more. 1, 2, 3, 4. It's like a bullseye. I used the circle tool and cheated. Alright, so I'm going to go ahead and put a point right, let me make this thicker, right here. And this point is 3 pi over 4 around the circle. It's not a unit circle, though. What's the radius of the circle that that's on? 4. I know, it's hard to see. And I'll call it, oops, I actually wanted to call this point C. So we say the coordinates in polar form for point C. It's on the circle with radius 4, and it's 3 pi over 4 around the circle. It's just another way of giving the location of a point. Turns out there's some things that are kind of convenient in this form. Yes?
If they just like, they'll always say polar coordinate for 3 pi, right?
Or there'll be something in the context of the problem. Yeah, that's a good question. Like, how do you know if it's in rectangular or polar if it's not told you? And yeah, it's going to have to tell you somehow. Especially if we talk about something like point A. What are the coordinates for point A in polar form? 3, 0. Wait, what? That's the same thing. That's crazy. Wait, what about this one? Let me put one over here. Point D. Point D in rectangular form. What are the rectangular coordinates for point D? Yeah, -2, 0. What are they for polar coordinates? 2 pi. Yeah. Now, with rectangular coordinates, there is only one correct answer. Polar coordinates, not so much. Yeah.
R can be more than just one, right? That makes sense. The radius of this would have to be, I guess there was one of 3, 1.
You mean like when you're drawing it?
Yeah. Does that change the value?
I'm not sure what you mean by that.
Like if the circle was smaller or bigger, the first one. If the increments was the one.
So you can make the scale be whatever you want, but the point is whatever scale you choose, point D is 2 units away from the origin. So, but there's other ways we could give point D. Now, before I give anything away, anybody have an idea where I might be going with this? Another set of polar coordinates that are still give me point D? Kieran? Yes. Because it still works. So we go to the circle with radius 2, and now if I go around 3 pi units, 1 pi, 2 pi, 3 pi gets me back to the same place. So, yeah, we could do that. We could also go backwards. This one's not very interesting, but if I go clockwise instead, negative pi will still get me to the same place. And here's the other crazy thing. R can be negative. This is one time I'm going to say, yeah, your radius can be negative. My radius is -2. Anybody have a guess where you think the angle might be? It's going to be 0. Very good. Yeah. So if you go to the ray of 0 radians, that puts you here. And then -2 just says go in the opposite direction of this ray 2 units. It still gets us there. So for instance, another way that I could list point C, I should have left space, but I'll put it up here. If I wanted to say -4 instead for the radius for point C, what angle could I use? Again, there's an infinite number of angles, but what's one angle I could use here? Do you have an idea? Kieran? Pi over 4? Do you want to let Adon do it? Adon, what do you think? Let's try -pi over 4. And again, there's different ways we could do this. So -pi over 4 would go in this direction. And then because of the -4, it says go in the opposite direction, which, oh, look at that, does put us on the correct ray. And now we're 4 units out. So, yep. Excellent. And we could also say just because our radius is negative doesn't mean that the angle has to be negative. So can anybody give me just one more using a positive angle? Gregory. 7 pi over 4. Let's try that. 7 pi over 4. Which quadrant does 7 pi over 4 go in? It goes in quadrant 4, so it's in the right direction. And then negative 4 means, for the radius, means we go in the opposite. So does that make sense how polar coordinates work? Any questions about that? Yes?
So if you wanted to find the polar coordinates of B, you just have to, like, use Pythagorean Theorem to find the radius and stuff like that.
That's the next thing we're going to do.
You can always just make whatever circle you want to appear as an end, right?
Yes. It's like magic. So yeah, how do we convert back and forth between them? So we have some nice formulas. Converting between Godzilla, rectangular and polar. So first of all, we can use something we've seen before. X is the same thing as r cosine theta, and y is the same thing as r sine theta. So back when you were learning about the unit circle, or just circles in general that had a different r, remember these formulas from then? We can use those same formulas now. And then Kieran was bringing up the Pythagorean Theorem, so that's a great way to help us find r. We can make a right triangle out of the x and the y coordinates and use the Pythagorean Theorem to find r. Theta's the tricky one. You have to be careful with theta. Anybody have an idea for a formula we could use if we wanted to find, knowing x and y, we want to find theta? In fact, you know what? Why don't we do it with point B up here? I'm going to draw it down below. So point B was at negative 3, 2. So negative 3, oh sorry, negative 3, negative 2, right? Oh my goodness, wait a minute. I'll bet that's me not writing it. Anyway, point B should be at negative 3, negative 2, not positive 2. Putting a negative there. Yeah, what if I wanted to find the coordinates here? So we know in rectangular, it's negative 3, negative 2. I want to convert that. Convert negative 3, negative 2 to polar. So we have to find r and theta. Anybody know what r is right now? Yeah. We can make that right triangle there. This is 3 units. This is 2 units. R, using this formula, gives us root 13. So what about theta? How are we going to find theta? Greg?
Well, we have equation with like x, r, and cosine theta, and we know x and r, so we can solve for theta with that equation.
Yeah, we totally could. We have this equation already. We know x is negative 3. We now know r is root 13. So yeah, we could solve this thing for theta. Let's do it. Cosine theta, negative 3 over root 13. I won't bother rationalizing because we're going to plug it in a calculator. So theta is cosine inverse negative 3 over root 13. Let's go. I'm going to go to my calculator. Make sure I'm in radian. All right. Whoops. cosine inverse. Oh wait, I forgot the root 13. Blur. Root 13, there's my r. Actually, wait a minute. I can't remember what it is. I gotta go. Cosine inverse 3 root 13. I was on the right track before. Now my calculator's off. Cosine inverse negative 3 over root 13 and close. 2.55. 2.553. 2.553. So, it looks like we could say in polar form, point B is r theta. That's not right, though. Karen, do you see it, or you have hand up for something else?
553 is less than 5. So, how do you get the radius to show up in the right quadrant?
Yeah. This is the problem. So, we haven't done anything wrong. We're just not done. 2.553 is in the wrong quadrant. Does anybody know why? What's wrong with what we just did then? Which quadrant is 2.553 in? Yeah. How did it put us in quadrant 2 when it looks like we did everything right? We should be in quadrant 3. Yeah.
Negative 3 over 313. 313 is positive y. Right? It's a positive y coordinate, but this goes in first. So it's going to put us in negative x, positive y.
That is true. There's another reason. What's the range for arc cosine? The arc cosine function has a defined output. In what range? 0 to pi. It's whenever we put cosine inverse on our calculator, it doesn't matter what we put in. So even if we made the y coordinate negative, it's still going to put us in the wrong quadrant. We're only going to get answers that are in quadrant 1 or quadrant 2, something between 0 and pi. So you have to watch out for that. If your point is not in quadrant 1 or 2 for doing our cosine, your calculator's not going to give you the right answer. So how do we fix this? I mean, we have something to work with now. We have 2.553. We can do something with that to get us in the right quadrant. So let's look at what's going on here. That's up here in quadrant 2. And this is saying that theta is 2.553. We want to be in quadrant 3, though. So with this particular answer, does anybody see what we could do? Yeah. So we could say that theta is negative 2.553. And sometimes, not very often, it's more in like trig books. When you get to calculus books, you won't see this. But occasionally, they might say put your theta is only between 0 and 2 pi. They want a positive angle. How can I make this angle positive if it wants us to give a positive angle? Yeah. Or adding 2 pi to this, however you want to look at it. Or theta is 2.553 plus pi, 2 pi, I mean. Go around a circle. And it'll get us to the same place. So, this wasn't quite right, but we were almost there. We could say negative 2.553, or I'm going to go ahead since we're in decimal. $3.729. That'll just truncate it. 3729. already forgot. What's 329? 729. Oh my god. I knew there was 3 though. And those will be the 2 most common answers people would give. So the bottom line is you just have to be careful. Think about which quadrant you're in. And there's nothing wrong with using something like x equals r cosine theta, or we knew y, so we actually could have used the y equation and gotten the same answer. What's typically given, though, is we know x and y like without having to find r first. So I'm going to go back up here to the equations I was giving you. Tan theta is y over x. That's the equation that is typically given, but you would not be wrong to use something like we did on this example, the x equals r cosine theta. If you did that on a test, you'd get full credit. You do that on the AP, you get full credit. It's mathematically valid, nothing wrong. But when you look at the equations, people typically use the tan. But you're going to have the same issue. Because what's the range for tan inverse? Excellent. Negative pi over 2 to pi over 2. So that's going to give you answers only in quadrants 1 and 4. So again, if your angle is in quadrants 2 or 3, you're going to have to adjust. The nice thing about using this version is the symmetry of tangent. So if we look at cosine and where cosine's positive and negative, it's positive in quadrant 1, then negative, then positive. So, you know, if you're in quadrant, you know, we have to do this reflection about the x-axis, which isn't that big a deal. It's basically making the angle negative. But with tangent, and I don't know, maybe it's not nicer. I think it's nicer. It goes positive, negative, positive, negative. So if your answer is in quadrant 3, but you get an angle in quadrant 1, all you have to do is add or subtract pi, always. And then the same thing if you're in quadrant 4 versus quadrant 2, you're off by pi. So to fix your angle with tangent, it's always add pi, add pi. What do you want to do? Add pi. Maybe subtract pi to get your angle in a certain range, but adding or subtracting pi always fixes it for tangent. You have to think about it a little more with cosine or sine. It's another reason I think people typically use tangent. But anyway, so that's converting back and forth. So if you're given polar, that's super easy. Just use these formulas. There's nothing you got to watch out for. But if you're given rectangular, you want to change to polar. R is straightforward. Theta, you just have to consider the quadrant you're in. So any questions about that? All right. The next thing, which may seem silly right now, but it actually, when we start doing the calculus with polar, this is going to become an important thing. I'm just going to give a couple of pictures here, and what we want to do is describe the shaded region using inequalities with r and theta. So we'll just do 2 quick examples. And because we're drawing these freehand, it's going to kind of give it away, but I'm going to start with, let's do 3 concentric circles. I'll do these freehand so they won't be as pretty. But my scale is 1. Each one of these circles has a radius of 1. This angle is pi over 6, so this one over here is 7 pi over 6. This guy's pi over 3. Oh my god, I just lost it. 2 pi over 3, 4 pi over 3. Then we have 2 pi over 3, and 5 pi over 3, And by the way, if you haven't seen polar paper, like we're used to rectangular coordinates, so we got the grid. You can get graph paper that's polar graph paper, and it looks something like this. Drawn nicer, of course, but it's 5 pi over 6. It's 11 pi over 6. And let's say that we are looking at this region right here. Now, it's actually not hard at all, but the directions just may be weird. So for this first one, I'll bet once you see the answer to the first one, though, you'll be like, oh, that's what they want? Oh, okay. Anybody have an idea what they want, though? So here's all they want. Look at the shaded region. Which angles is that shaded in between? So it goes from pi over 6 to 2 pi over 3. What about radius then? What's the radius shaded in between? 1 to 3. That's all they want. Literally. It's not that bad, is it? So, if I want this region, this pink region, oops, keep doing that, pink. Anybody want to give me one of the inequalities now that you know what it's asking for? Pi. I heard pi. Thought. Yeah. Less than or equal r less than or equal to 4 pi over 3. Is that right? Good. What's r? Yes. Yes, Gregory.
It's always going to be like less than or equal to, and it's never going to be just less than or greater than.
Yeah, they would, I mean, for what we're going to do, we're not really going to worry about that, but if it really was just this, they would put dotted lines like we're used to seeing when we don't want to include the endpoint. Any other questions on that? Be careful, though, because if I said shade where, let's say that r is going to be between 2 and 3, and theta is going to be between negative pi over 4 and pi over 4, just so we're clear. One, 2, 3, and then we know pi over 4 is here, and negative pi over 4 is here. And let's see, shading between 2 and 3, so I'm only going to shade here. Oh, that's kind of a thick one. There we go. I have shaded where the radius is between 2 and 3, and I shaded in between negative pi over 4 and pi over 4. Or have I? Yeah, what's wrong with what I did? Yeah, these values are not in between negative pi over 4 and pi over 4. That's the unshaded part. So watch out for that. A little thing right now become bigger when we do this. All right, the last thing is, what about graphs? So we know how to plot points, but what about actual graphs of curves? Polar gets kind of fun. If you've never played around with polar curves, they're kind of fun. All right, any questions so far? Alrighty, let's see. Let's do this first. Example. Without actually looking at any pictures right now, let's convert the following equations from polar to rectangular, or, oops, I can't spell rectangular, or the other way. We'll go back and forth. If the problem says xy, we want it in r theta. If the problem says r theta, we want it in xy. Let's start off with the easy ones. When you start with rectangular, xy equals 1, for instance. I want to write this in polar. I said this is easy. How is this easy? Anybody know what we do? Why is this easy? Remember those equations I gave you for converting the coordinates? We use those. X was r cosine theta. Y was r sine theta. And that's like literally it. R squared cosine theta sine theta equals 1. If it's nice, we typically solve for r, but it's not always nice, so you won't always solve for r. As far as like if it's a free response question, how do you know which way to put your answer? Just, you know, with the trig involved, make sure you simplify the trig part, but there's no real standard. If it's multiple choice, obviously go for what's in the multiple choice. I am going to solve for r squared, though. We can do that nicely and say that r squared is 1 over cosine sine, or we can just say secant theta cosecant theta. But that's literally it. So when you're going from rectangular to polar, you can use those formulas. X equals r cosine theta, y equals r sine theta. If you're going the other way, though, it's not always as straightforward. Like let's do this one. R equals 2 sine theta. And the problem is theta. And I'm going to go back up here for a second. Because I can't just take this equation with theta and solve for theta and say theta is tan inverse of y over x because of what we saw. What if you're in quadrants 2 or 3, tan inverse theta is not going to cut it. But it will cut it when you're in quadrants 1 and 4. But we don't know which theta, where theta is, because we're not actually putting a value in for theta. So how do we know if we add pi or we don't add pi? Holy crap. The bottom line is you can't use this. So what do we do? I don't know. So here's what we can do. Actually, before I give it away, anybody have an idea? And it really, I mean, each problem's a little different, but anybody have an idea with this one? Well, here's what we can do. Look what happens when I multiply both sides by r. I get r squared equals 2 sine theta times r. How did that help us? What? R squared over 2 equals y. R squared over 2. Where are you getting the y from? Explain it to us. There we go. So that takes care of the right-hand side. That takes care of the theta. What am I going to do with r squared over 2? Remember? this formula, the Pythagorean Theorem? R squared is x squared plus y squared. I know, right? So each one of these problems is a little different. You just kind of have to play around with it. And again, how do you leave your answer? Because these are often not functions. You often can't solve for y. Make it look nice, I guess. There's really no standard. I mean, if you happen to spot like, oh, it's a circle, I'll put it in standard form for a circle, or something. But if you don't see what it is, I don't know. By the way, what shape would this be? Because it's x squared plus y squared equals 2y. Not just 2. I mean, if it was 2, it would be a circle. I don't know what you're drawing, Gregory. Oh, it's this thing. Yeah, right. Well, you know what we can do? We can graph it. R equals 2 sine theta. Remember how I showed you your calculator could do parametric? It can also do polar. Same way, if you go into mode, right next to parametric is polar. And then once you change it to polar, your y equals looks different again. What? Now, this is going to be a drawback of these calculators, because these calculators can only do it when it's solved for r, just like it can only graph equations solve for y. So if you do have something like our first example said r squared equals like our final answer, you'd have to do plus or minus. You'd have to take the square root and do plus or minus and do it in 2 different ones. But this one just said r equals 2 sine theta. And again, to get theta, all I have to do is hit that button we're used to hitting for x. Now it knows we're in polar form, so it's going to put a theta in there. And I don't know what my window is. I'm just going to, do I want to do, let's just hit graph. We'll see. It's a circle. Wait a minute. It's actually a circle. You can, I don't know if you guys know this. If I go to zoom, where is it? Look at choice 5. It says square. So what'll, before I go there, if you look right now, see how the, like 1 unit on the x-axis is much longer than 1 unit on the y-axis. So it's going to stretch pictures out like this. But if you don't want it to, if you do zoom square, it will fix the scale so that the scale is the same on the x and the y. It actually is a circle. Wait a minute. It's a circle, but it didn't equal 2. It equaled 2y. What the heck? I'm going to go back here for a second. Do you remember completing the square to put your things in standard form? You won't have to do this, but just a quick reminder. I'm going to go ahead and put that 2y over. And now I'm going to complete the square. Got to add 1, so we add 1 here. And so it's x squared plus y minus 1 squared equals 1. It's just the center's not at the origin anymore. It's still a circle. Circle, center is at 0, 1 with a radius of 1. And if I go back to my graph, that's exactly what it was. Center's at 0, 1, radius of 1. So speaking of that, the last thing, handy equations to know. Oh wait, no, there's one more thing that I want to do. I'm like, where is that? Wait, yeah, there is one. But let me go ahead and give you the handy equations to know, and then I'll give you the last thing. Handy equations to know. So let's talk about circles. If you got a circle centered at the origin, with a radius, and I'll call the radius capital R because lowercase r is already taken. Anybody happen to know what this is? Just out of curiosity, based on what you've seen. Say it again. Yeah, well, yeah, what would it be in polar form? It would literally just be R equals R. Because you want every single point on the circle with radius R, which makes a circle with radius R. I know, it's crazy, isn't it? But if you move off the origin, like we just did. So a circle centered at A0 with radius A, that is R equals 2A cosine theta. And if you move the center to 0A with radius A, that's R equals 2A sine theta. And then the only other one that is good to know, I mean, there's a lot of them. There's like flowers and stuff with so many petals. We won't get into all of that. But let's just do a line through the origin. With a slope of m. So this is very similar to the circle one, but this time the angle is constant. If it's going through the origin, then the angle it's making with the x-axis is always the same. So it's just theta equals tan inverse of m. And that'll actually take care of both directions because r can be positive or negative. And so when it's negative, it'll give it in the opposite direction. All right, so the last thing I want to know is let's try graphing by hand a kind of funky looking polar, and then we'll see if we got it right. So the grand finale. Graph this. Let's do R equals 2 cosine 3 theta. So the one thing I didn't actually cover when we were doing like just giving coordinates of points. What would be the coordinates in polar form of a point at the origin? What's R? What's theta? Anything. Yeah. You can make theta anything you want. 0, anything, and polar is always at the origin. You could say go 0 units from the origin around 7 pi over 209 if you wanted. You're still just at the origin because you haven't moved off. So yeah, theta can be anything. So when you're graphing by hand, instead of x and y intercepts necessarily, what's kind of nice, I mean they can be good too, but also just where it's hitting the origin. Because what happens is these things often loop back on themselves and they make these really cool curves. So we could find where this thing hits the origin, where it's going to equal 0. We could find when it equals pi over 2, when theta is pi over 2, or pi, or any of those. We could see what happens. I don't know. Or we could just pick a bunch of points, plug them in, and see. So let's do this. Let's make a table. All right. Now, because of that 3 theta, we're going to need a lot of points to see this. I mean, we can start with the basics. We can start at 0. Oh, but 0 for theta, sorry. If I put 0 in for theta, what does r equal? All right. I'm going to skip some spaces because I think we're going to need some stuff in between. If theta's pi over 2, what's r? Yep. If r is pi, what did you say? Negative? And then 3 pi over 2? See, that's be 9 pi over 2, which is the same thing as pi over 2. And then 2 pi. All right, let's see what we got. Let's see what this gave us. And if it didn't give us much, we got to look in between. All right. So 2, 0. That's going to put me right on the x-axis. 0 pi over 2 puts me at the origin. Where does negative 2 pi go? How does that negative thing work again? Yeah, it actually puts me right back at the same point. And then 0, 3 pi over 2, and then 2 pi. For 5 points, it really only gave me 2. That's not useful, is it? So is that all this thing is doing? It's just bouncing back and forth? Or is it bouncing like this? I don't know. I think we need some more points. Maybe, right? So let's go for pi over 4. Let's see what happens there. Now, actually, let's go to the graphing calculator. But, yeah, because you got to watch out for just like relying on a couple of points. So let's see what this thing looks like. So it was a 2 cosine 3 theta. 2 cosine 3 theta. And there's a whole lot more going on than just those 2 points that we found. So this is a rose. And you can play around with, if I go back here, and I put in 4 theta. But if I put in 5 theta. So basically, if you think of it as cosine n theta, if n is odd, you'll have n petals. But if n is even, you actually get 2 n petals. If I go back here and make it 6, we're going to get, there's 12 petals in there. I know, right? You can do some really fun things. So anyway, so there is like a whole thing about how to know when it's a rose. There's other shapes too, like lemniscates, and I've never known how to say that word, but I think that's how you say it. But there's a whole bunch of different ones. But anyway, we're going to be looking at next class. Well, not next class, because next class is your work day. Next time we have a lesson is going to be, what if I want to know the area inside one of those petals? We're going to see how to do it. Anyway, that's the end. That's all I got for you. Any questions? All right.